a recipe, a GPS route, a knitting pattern. All three are the same thing wearing different clothes. A precise sequence of steps that takes you from a starting point to a finished result, reliably, every single time you follow it. That's an algorithm, not some mysterious piece of computer wizardry. Something you've been using your whole life in the kitchen and on the road, long before you ever touched a computer. Today we open up what an algorithm actually is and why every single thing covered in parts 1 and 2 of this series runs on top of 1. Welcome back to the Artificial Intelligence Institute Africa, Aiia, Ubuntu Guild's videos on AI. I'm Dr. Dennis Magaya. This is part 3 of our What is AI series. Parts 1 and 2 covered what AI and machine learning are. This video goes one level deeper into the actual mechanism that makes any of it run at all, the algorithm. Before we dive into the details, let me show you the road ahead. We are covering 3 layers today. Layer 1 is the core definition, what an algorithm actually is. This is the lifeline you must lock in. Layer 2 is the landscape, the 5 major families of algorithms and what problems each one solves. Layer 3 is the real world, where to actually find algorithms, who builds them, and how to use one in practice. Layer 1 is your foundation. Layers 2 and 3 are your toolkit. Let's start with Layer 1. Here's a definition worth holding on to. An algorithm is a finite, clear sequence of steps that takes some input and reliably produces a specific output. 3 words in that definition are doing all the work. Finite, it has to end, it can't run forever. Clear. Every step has to be so precisely specified that there's no room for different interpretations. And reliable. Given the same input, it produces the same output every single time. Recall the cold open. A recipe is finite. It ends when the dish is done. Clear. Crack 2 eggs, not some eggs. And reliable. That's the whole definition, already familiar long before any code enters the picture. Said even more simply, an algorithm is just a precise recipe for solving a problem, spelled out clearly enough that anyone or anything following it correctly will always land on the same result. Here's the problem algorithms actually solve. Tell a friend, just head toward town, you'll figure it out. A human can handle that vagueness, filling gaps with judgment and common sense. Give that same vague instruction to a computer, and it does nothing at all because a computer has zero capacity to figure it out from a vague instruction. It can only execute exactly what it's told, one precise step at a time. That's why algorithms are needed. Computers require completely clear step-by-step instructions to do anything whatsoever. There's no such thing as a computer using common sense to fill in a gap. Beyond that strict necessity, algorithms bring 3 further benefits. Consistency. The same algorithm produces the same result every time. Speed. A well-designed algorithm can process in milliseconds what would take a person hours. And scalability. An algorithm that sorts 10 items and one that sorts 10 million items can be the exact same algorithm. But here is the hidden trap. Not all algorithms scale equally well. An algorithm that sorts 5 numbers in a split second might take 1,000,000 years to sort 5 million numbers if it's the wrong kind. This is called algorithmic complexity. Computer scientists use something called Big O notation to describe how an algorithm's runtime grows. Choosing the right algorithm isn't just about whether it works, it's about whether it can finish before the sun burns out. That is why in practice you always match the algorithm to the scale of the problem, not just the problem itself. Say it back in plain words. Algorithms exist because computers can't guess what you mean. But choose the wrong one and it may never finish. Algorithms aren't one single kind of thing. They split into distinct families based on the kind of problem they are built to solve. 5 categories matter most for this course: sorting and searching, graph optimization, heuristic, and recall part 2, machine learning algorithms. Sorting algorithms take a collection of items and arrange them into a defined order. Searching algorithms find a specific item within a collection as efficiently as possible. These two are used constantly and invisibly. A database sorting search results by relevance. A phone's contact list kept alphabetical. A search engine finding one relevant page among billions. A graph here just means a network of connected points, cities connected by roads, people connected by friendships, web pages connected by links. Graph algorithms find useful structure within that network. The shortest route between two cities, the fewest connections between two people on a social network, which web pages are most central to the web. GPS navigation, social network recommendations, and search engine ranking all run on graph algorithms underneath. Optimization algorithms search for the best possible solution among a huge number of options according to some measurable goal: lowest cost, shortest time, highest profit. A delivery company deciding the order to visit 50 addresses, an airline pricing seats to maximize revenue, a factory scheduling machines. All optimization problems solved by algorithms designed to search enormous option spaces efficiently. Some problems are so large that finding the mathematically perfect answer would take longer than the age of the universe. Heuristic algorithms trade perfect accuracy for a fast, good enough answer. A chess engine can't check every possible sequence of future moves, so it uses rules of thumb to focus on promising ones instead. This trade-off, speed over perfection, shows up constantly in real-world systems where an exact answer simply isn't reachable. And here's the direct link back to part 2. Every single technique covered there, regression, decision trees, K-means, autoencoders, is itself an algorithm, just one whose exact steps are partly learned from data rather than fully specified by a human in advance. This is exactly what part 1 called statistical AI. Instead of a human writing the rule directly, an algorithm infers it from patterns in data. But machine learning algorithms aren't just one big pile. They are organized into a clear, hierarchical framework. Once you see this structure, you'll be able to place any new ML algorithm you encounter into the right mental box. At the very top, machine learning algorithms split into 3 broad paradigms based on the kind of data they get. Supervised learning algorithms learn from labeled examples. Each piece of training data comes with the correct answer attached. The algorithm compares its prediction, calculates the error, and adjusts itself to make that error smaller. These split into 2 main types. Regression predicts a continuous number, like a house price, tomorrow's temperature, or blood pressure. Common regression algorithms include linear regression and more advanced ones like gradient boosting and random forest regression. Classification predicts a category or label, like spam or not spam, cat or dog, or which disease a patient has. Classic classification algorithms include logistic regression, decision trees, random forest classifiers, and support vector machines. Unsupervised learning algorithms work with unlabeled data. There is no correct answer provided. Instead, the algorithm must find structure and patterns on its own. This splits into clustering and dimensionality reduction. Clustering algorithms like K-means group similar data points together. Dimensionality reduction algorithms like PCA and TSNE compress complex data while preserving its essential structure used for visualization and preprocessing. Reinforcement learning algorithms learn by interacting with an environment, receiving rewards or punishments, and adjusting their strategy to maximize reward over time. These power everything from game-playing AIs to robotic control systems. The core family here is Q-learning. Now, here is the most important branching point within supervised and unsupervised learning, the split between statistical machine learning algorithms and neural network algorithms. They are relatively interpretable. You can usually understand why they made a prediction. They require less data to work well, and they are computationally efficient. They are the workhorses of industry, used in credit scoring and medical diagnosis. Neural network algorithms, also called deep learning, are the other major branch. These are algorithms that learn through layers of interconnected artificial neurons. Neural networks are less interpretable. They are the black boxes we covered in part 4. They require massive amounts of data and demand significant computational resources, GPUs often, but they excel at problems where statistical ML struggles, image recognition, natural language processing, and extremely complex high-dimensional tasks. CNNs are specialized for grid-like data, images, and video. They learn to detect features like edges and objects hierarchically. RNNs are designed for sequential data, time series, text, speech. They maintain a memory of previous inputs. LSTMs and GRUs are advanced RNNs that solve the problem of forgetting long-term dependencies. And at the very top, we have the transformer architecture, the foundation of GPT, Gemini, and Claude. Transformers use attention to weigh different parts of the input simultaneously. Now, to go one level deeper, neural networks. The architecture behind our RNN, CNN, and Transformer series are actually built from several algorithms stacked together, not just one. At their core, they run on three essential algorithms that form the engine of learning. The forward pass is an algorithm in its own right, turning input into prediction. Backpropagation is a second algorithm, calculating how much each weight contributed to error. And gradient descent is a third algorithm, specifying exactly how to adjust each weight once error is known. A trained neural network is the product of all three algorithms running together. All neural networks are machine learning, but not all machine learning is neural networks. If ML is a toolbox, neural networks are the most powerful tool in that box. But sometimes a simpler tool, like a decision tree or linear regression, is all you need, especially when interpretability or limited data is a concern. You don't use a sledgehammer to crack a nut. Classical AI algorithms sit completely outside the machine learning circle. They don't learn at all. A basic calculator doesn't get better at arithmetic the more you use it. It just executes the same fixed rules. A traditional algorithm's steps are fixed. A machine learning algorithm's steps adjust themselves, but both are still a finite, describable sequence of operations. To make this concrete, here is how you would match common problems to the right algorithms. Predicting house prices or spam versus not spam can often use simple regression or decision trees. Customer grouping uses k-means. Object recognition, translation, or playing chess requires the more powerful neural network architectures. ML splits into supervised, unsupervised, and reinforcement learning. And within each, you choose the complexity that fits your problem. Before covering how to use an algorithm, it's worth answering a more basic question. Where does one actually come from? You very rarely invent an algorithm from scratch. Almost every problem you'll ever face has already been solved by someone else, and that solution is sitting somewhere waiting to be used. Academic textbooks are the classical source, but open source libraries are the practical source most engineers use day to day. Programming languages ship with standard libraries containing pre-built, battle-tested algorithms. Most of the time, you don't download an algorithm's raw code. When you write list.sort in Python, you aren't writing a sorting algorithm. You are commanding a massive, highly optimized algorithm that already exists. You call them standing on the shoulders of giants. Computer scientists and mathematicians design new algorithms, software engineers implement and optimize them, and research communities refine them over years. Almost every algorithm you'll ever need already exists in a library or tool you use every day. Using an algorithm follows a consistent process. First, define the problem precisely. Second, choose the right existing algorithm based on the problem and scale. Third, prepare the input format. Fourth, run it. Fifth, check the output against what you actually needed. Let's run a sorting algorithm on 5, 2, 8. Compare 5 and 2. Out of order, swap them. 2, 5, 8. Compare 5 and 8. Already in order, no swap. One full pass, no swaps needed on the second comparison, and the list is sorted. That's it, a real algorithm. Let's bring it all home. Every architecture in our RNN, CNN, and Transformer series is, underneath everything else, an algorithm. A sophisticated one, but built from the same basic idea covered in this video. Thank you for watching this Artificial Intelligence Institute Africa AIIA video brought to you by Ubuntu Guild. Subscribe to our AIIA YouTube channel and to Cognify.